The next topic that we want to talk about is called linear approximations. So we've already talked a lot about what tangent lines are relative to a function because that's what a derivative is, right? It represents the instant rate of change or the slope of a tangent line. We're going to use the relationship between the tangent line and the function in order to approximate values. Let's take a quick look at this graph just so you have an idea of what we're looking at. This is our tangent line, obviously, and this was just an example of a random function that we're dealing with. What we're going to look at is because tangent lines are so close to the function in this general area, right around where the tangent line actually touches the function, we can use the tangent line to approximate values on the function if we're close enough to that spot where the tangent line touches. So in here, I'm going to get pretty decent estimations by using information about the tangent line. Now I start getting out here and I'm approximating values for f of x. There's a good distance here, right? That's not going to help me. But from here to here, if you'll notice, you couldn't quite tell exactly what that was looking like. But this idea from this spot at the top to this spot at the bottom, right? Those are pretty close to one another. So the tangent line is going to give me a good approximation for that. So let's talk about how that's going to work. Start with information that we know. We know the point slope form of a line. Y minus y1 equals m times x minus x1. That's how we write the equation of a tangent line. But because we're calculus students, let's look at that with slightly different notation. Let's look at that as y minus f of a being for a particular value. We're going to call that x value a, equals m, which is the slope at a, because we're now a calculus students at this point, times x minus a. So all of this, right, this is thinking like a calculus student here. Recognizing the connection between this point slope form that you've worked with since algebra and now connecting it to the calculus that we've done. When we're using a tangent line to find an approximation, we might want to rewrite the order of this. So this is the equation that I'm going to be referencing, but this is the value that I'm actually going to be trying to find. So I'm going to move this f of a over. We're going to say y is equal to f of a plus f prime of a times x minus a. That's just a little algebraic rearranging. And this note, I think, is valid in terms of understanding exactly what we're writing down. So y represents the y coordinate on the tangent line. We are going to have information about the tangent line. And that's what we're going to be using. And this gives us an approximation. We are not dealing with an exact value for this, so we're going to use lots of those little squiggly estimation signs of f of a. The y-coordinate of a on the function f of x is represented by f of a, and f of a is the actual value of the function. Let's talk about what this looks like. I think once we do an example of this, it's gonna make a lot of sense to you. It's gonna be very logical and broken down. I am given a function x squared. Pretty familiar with that. I want to write the equation of the tangent line of f at x equals 1. We've written lots of equations of tangent lines at this point. I need a slope. I need a point. So let's start dealing with slope here. The derivative of x squared is 2x. I need a point and a slope at 1. So f prime of 1 is 2. And f of 1 is just 1. So again, I'm dealing with part A. I'm just writing the equation of a tangent line. So y minus 1 is equal to the slope, which is 2, times x minus 1. This is your x comma y, which came from our xy here. So that is the equation of the tangent line. This is where this approximation piece really comes in. So we're going to use that information to approximate a value for f of 1.01. Now, like we did earlier, I may want to rearrange where the y is by itself. So I'm going to go ahead and rewrite this as 1 plus 2 times x minus 1. And remember, I'm going to use this tangent line to approximate the value of f at 1.01, which is very close to that tangent line. So going back to this picture, I'm really, really close to that one specific spot where we would be touching the function and the tangent line would be the same. So I'm close enough that the tangent line is going to be a really good approximation. We do need to indicate that it's an approximation. So I'm going to do f of 1.01 is approximately. Notice that I'm using an approximation sign, not an equal sign. And now I'm going to go back and I'm going to use this information to plug in. So I'm going to say 1 plus 2. And the x value that I'm looking to evaluate at is 1.01. This is the equation of the tangent line. We are using that equation to evaluate f at 1.01. Now all I need to do is simplify this. So this is going to be 1 plus 2 times 0.01. So this is 1 plus 0.02. This is my approximation. Remember, long ago people didn't have calculators, so approximations were very important to getting close. What this represents is an approximation or an approximate value of f at x equals 1.01 using the tangent line. So it's not the exact value, but it's really close. Now, because I have enough information and I also have access to a calculator, which is very handy, I'm going to find the exact value using the function. So if I wanted to find the exact value just to determine how close I was, I would plug in a 1.01 in for x into the original function. You can do that by hand, but obviously you have access to a calculator. So this is what we would get for my exact value. So one of the big takeaways here is, what is my error? How close am I? Whenever I do an approximation, how far away am I from the actual answer? So understanding your error really matters here. And the error is always going to be equal to the exact value minus the approximation, but the order of that doesn't really matter, so we put absolute value signs around it because we want to know what just the difference between these two are, but it doesn't matter if it's negative or positive. So let's look at that. Equals 1.0201 minus 1.02. I want to know the difference between those two. If I subtracted those, that's pretty close. That's 1/10,000th. So because my tangent line, I use my tangent line, and that decimal is so close to 1, I am very accurate in terms of my approximation. My approximation is within 1/10,000th of the actual answer. So depending on what I'm dealing with, that might be close enough. That's how we work with tangent line approximations.